Okay, let's continue our discussion of inequalities. So we have any vector space with an inner product. And last time I stated the Cauchy-Schwarz inequality, which said that the absolute value of the inner product of two vectors is less than or equal to the product of the length of the two vectors. Okay, and that's true in any inner product space, and that's an important inequality called the Cauchy-Schwarz inequality. And maybe I'm forgetting a T in Schwarz, I can't remember. And the second inequality I didn't get to yet, but I'll mention it now. Or maybe Ed mentioned it, but anyway, here it is. It's the called the triangle inequality, which is the length of v plus w is less than or equal to the length of v plus the length of w. And this, of course, in R2 is just the usual triangle inequality, so that's what this is called in general. So let me talk a little bit about these two inequalities some more. So one thing I want to emphasize is that these are inequalities for any inner product space. So you're certainly allowed to use your intuition from R2, but you have to keep in mind that it's true in general. So here's an example. As I mentioned last time, the Cauchy-Schwarz inequality in R2 with the usual dot product is that that if you take the dot product of two vectors, that's equal to the product of the lengths times the cosine of the angle between the two vectors. And in R2, that basically tells you the Cauchy-Schwarz inequality, because the cosine, of course, the absolute value of cosine of theta is less than or equal to 1. So if you take the absolute value of both sides of this equation, you get this. And well, in general, so you have a general V and a general inner product. You can define the angle, or the cosine of the angle, by this formula to be the length of VW, sorry, the absolute value of VW over the length of V times the length of W. What do I mean by that? Well, we just have an arbitrary vector space and with an inner product, and there isn't really a notion of angle yet, and this is how you define it. And this makes sense because this number, the absolute value of this right-hand side, is less than or equal to 1. So it makes sense to call that the cosine, or if you prefer, another way to say it is to say that you define the angle to be the inverse cosine, or arc cosine, of that right-hand side, and that's well defined because the number is less than or equal to 1 in absolute value. All right, let's talk a little more about the Cauchy-Schwarz inequality. So that says that in any vector space you have VW is less than or equal to the length of V times the length of W. And let's put some arrows over here. So I'd like to prove this, give the proof of this fact. I'm not going to give that many proofs in this course, but this is an important one. This is a very fundamental inequality. And it illustrates something interesting and important, which is how on earth are you going to prove this thing? I mean, in R2, it's just some trig inequality that you can figure out, but you're in some abstract vector space here, and you hardly have anything to use, so how could you possibly prove this? Well, that's why it has somebody's name attached to it. It's not entirely trivial, but the proof is actually kind of neat. So let's look at it. So we're going to take any vectors v and w, and I'm going to let t be an arbitrary scalar. And I'm going to consider the following thing. Take v plus t times w and squared. So this is the length of the vector v plus t times w. So what that is the vector v plus some multiple of the vector w, so it's some vector along this line. And I'm looking at the squared length of that vector. Well, what is that? That's, by definition, this norm is v plus tw, v plus tw. And what is that? We can work this out. Well, there's a v term, which gives me vv. And there's a tw term, which gives me t squared times w. And then there's some cross terms. There's v tw, and there's also twv. And both of those give you both of those give you t times vw. And so when you add them up, you get a 2. So I'm going to write this thing is greater than or equal to 0. Okay, so let's simplify this a little bit. Let's call this A. And let's call this number B, and let's call this number C. So this says that 0 is less than or equal to C plus 2bt plus AT squared. Okay, and so this is a quadratic form. This is a quadratic function here. Call this thing f of t on the right hand side here. And what I'm saying is that this function is greater than or equal to 0 for all values of t. Now let's draw a little picture. What is going on here? So here's t, and here's f of t. What does this function look like? Well, it's a quadratic, so it's a parabola, and it must be pointing up and somehow be above the x-axis. So this is what it looks like. And it's interesting to look at this minimum here, the minimum point. So where is the minimum? So let's put on our calculus hats and remember, how do you find the minimum, the place where this function takes on its minimum? Well, I'm sure you all remember, you take the derivative. And the derivative of this function is 2at plus 2b. And you set that equal to 0. And you find that the minimum is obtained where t is equal to minus b over a. And what is that? What was b? B was VW over A, which was WW, which I'll write as the length of W squared. Okay, so this value of t is where this function is. All right, so let's write this down again. I had this equation: 0 is less than or equal to c plus 2bt plus I think it was at squared, and the minimum was where t was minus VW over the length of W squared. So let's plug this in here. And what we get is that 0 is less than or equal to 0 is less than or equal to c, which was v squared, if you go back to the previous page. And now we're plugging in t here. We're going to get minus 2 VW squared over the length of W squared. And the last term is going to be VW squared over W squared. So these two terms are the same, except for the 2. And so if you rearrange terms, you find that VW squared over the length of W squared is less than or equal to the length of V squared. I'll put the arrows back. So, okay, so that's just bringing, combining these two terms and bringing them to the other side. And that's it. You just bring this up to the other side to get the inequality. VW squared is less than or equal to V squared W squared. And now I have squares everywhere, so I can take the square root of the whole thing. And you just, when you take the square root, you're taking the positive square root. So on the left-hand side, you're getting the absolute value of VW. And, well, the length of V is positive, so you don't need an absolute value there. And similarly on this other term. And that's the inequality. All right, so what's the moral of the story? All I used was the bilinearity, the formal properties of the bilinear form. The only thing I needed was that this form is bilinear and symmetric. Well, and of course also positive. I used that at some point. So the important thing is that we proved the Cauchy-Schwarz inequality without using anything except for these three crucial properties of the bilinear form. Okay, so let's look at some examples, and what I'd like to look at is this version of the Cauchy-Schwarz inequality. So remember I mentioned last time that even though you're in a higher dimensional vector space, if you take this vector v and this vector w in whatever vector space you're in, the span of v and w is two-dimensional, and so it makes sense to talk about the angle. But be careful, even if you're in R2, how do I say this? This is a little warning sign. Even if you're in R2 itself, if it's possible that VW is not just V dot W. It could be something else, in which case this notion of angle is not the familiar one. But that's okay. It's the cosine of the angle in this funny inner product. So anyway, so let's do a couple of examples of that. So suppose you're in Rn, and I took the following two vectors. So I took one vector like this, and the other vector similarly. So I should have written this here with a dot, dot, dot. So what I'm taking is two vectors with a 1 and a -1 in that order, a 1 followed by a -1, and they're allowed to be anywhere in this Rn. What can you tell me about the cosine of the angle between these two vectors? Well, you compute this number, VW, over the length of V and the length of W. Well, what's the length of V? By definition, that's the square root of the sums of the squares of the coordinates, which is to say 1 plus 1, which is radical 2. And the length of W is also radical 2. So the product of those two lengths is 2. So this angle that I'm looking for, this cosine of theta, is the inner product of these two vectors divided by 2. Oh, I'm sorry, I forgot to say Rn with the usual dot product. That's why I put this. And I'll write this as V dot W over 2. Well, what is the dot product of these two vectors? There's a couple of possibilities. If the 1's and -1's are in different places, V dot W could be equal to 0. Let's see, if this 1 and this -1 lined up, it could be equal to -1. And the same thing would happen if this 1 and this -1 lined up. And if they all lined up, if these guys matched and these guys matched, then what I'd be getting is 1 plus 1 is 2. So that says that the possibilities for the cosine of theta are 0, -1/2, and 1. What does that tell you about theta? Well, I'll write it right here. That says that theta is equal to, well, 0 that means they're perpendicular, which is to say 90 degrees, or as we like to say, pi over 2. And how is cosine equal to minus a half? Where does that happen? I'll let you refresh your trigonometry memory, and that's at 2 pi over 3. And, of course, cosine theta is equal to 1 when theta is equal to 0. And so what did we get here? We got theta, the possibilities for theta were pi over 2, 2 pi over 3, or 0. And 0, of course, where, well, let's do this one first. That's where the two vectors are orthogonal. And 2 pi over 3, what does that look like? If you think about it, if this is one vector, then 2 pi over 3 is, you divide the circle up into 3 equal parts. That's the two vectors there. And then, of course, this last one is just where the two vectors are equal. And this is all going on inside some n-dimensional vector space. But any two of these vectors, they're basically just going on inside R2. And so it really does look like this. And this thing that I said about if it's not the dot product isn't an issue here. This is your standard dot product in Rn or in this R2 that we're talking about. So it's safe to really think of these as being orthogonal in the usual way. All right, well, let's go on and talk about the triangle inequality. So everybody knows that if you draw a triangle and it has sides A, B, and C, that C is less than or equal to A plus B. And, well, this is just the vector version of that. If you have a vector V and another vector W, then this vector is V plus W. And the length of this vector is the length of V. And the length of this vector is the length of W. And similarly here, you're getting the length of V plus W. So to say C is less than or equal to A plus B is exactly the same thing as saying that V plus W is less than or equal to the length of V plus the length of W. All right. So the proof of this is quite nice and simpler than the Cauchy-Schwarz inequality. Actually, this is a consequence of Cauchy-Schwarz. But anyway, see, I'm not going to do this one, but I recommend you look in the book. And it's theorem 3.9. And again, this is true for an arbitrary inner product. It's worth writing down the function versions of these because this often comes up in practice. And so suppose we're talking about functions on the interval from 0 to 1, and we're talking about continuous functions, and we define the inner product of two functions to be the integral of f of x g of x dx from 0 to 1. I mentioned this as an example before. This is a perfectly good inner product. And Cauchy-Schwarz and the triangle inequality apply here. Even though this is an infinite dimensional vector space, it's not Rn or anything, it's just an infinite dimensional vector space, but the proof worked. That's one of the beautiful things about it. Everything about the proof was true. And so what does the Cauchy-Schwarz inequality say? So the Cauchy-Schwarz inequality says that the absolute value of this side, which is to say the absolute value of the integral of f of x and g of x dx is less than or equal to the integral of f of x squared dx and the square root of all of that, and then the similar thing, the square root of the integral of g of x squared dx from 0 to 1. Right? Because this is fg, and this is the norm of f, and this is the norm of g. And remember, the norm has a square root in it. It's the square root of the f, square root of the inner product of f and f. And so let's look at this just for a second. This is not an entirely obvious fact. If you have two functions and you integrate the product, never mind the absolute value for the moment, suppose they're positive or something. If you integrate the product, that's less than integrating one of them, the square of one of them, and taking the square root and the square of the other one. And the triangle inequality becomes something rather non-trivial, which is that if you take the integral of f of x plus g of x, quantity squared, and the square root of that is less than or equal to the square root of the integral of f of x squared plus the square root of the integral of g of x squared. And all these integrals, of course, are from 0 to 1. And let's see, let's just stare at this for a moment. What does it say? When you add these two and you do the integral, it's going to be smaller than if you do them separately. So that's a good place to stop, and I'll do some examples in class. See you tomorrow.